Hello everyone, I'm Mighty, your hands-on practice assistant. In this session, we'll go through a CFD simulation together step by step and follow along with the practice example. The topic of today's practice example is LPipe fluid flow analysis. What is internal pipe flow analysis? It is a numerical simulation used to predict the velocity and pressure distribution of fluid flow inside a pipe system. After the simulation, you will be able to review results such as the airflow behavior in the pipe, as shown here. Before we begin today's practice, let's first summarize what we will be covering. After briefly reviewing the analysis model and boundary conditions, shall we begin following along together? First, after running NFX, click New button in the upper left corner to create a project. Then verify the unit system and click OK. Now, let's import the model. Click Import in the Geometry tab to open the CAD file. Once the model is loaded, right-click in the workspace and select Hide All Guides. If you look at the model tree on the left, you can see a LPipe. In general fluid flow analysis, you usually need to extract the fluid domain separately. This can be created easily using the CFD Volume Extraction feature. First, we need to create surfaces at the inlet and outlet of the pipe. In the Geometry tab, click Surface and select Make Face. Then, select the edges at the inlet and outlet of the pipe to create two faces. Next, click CFD Volume Extraction from the toolbar and select the pipe as the bounding box target. For the length, width, and height values, enter 0.3 meter, which is sufficiently larger than the pipe dimensions. Then, select the two faces created earlier as the closing faces. Click OK, and a large box with dimensions of 0.3 meter by 0.3 meter by 0.3 meter will be generated. The CFD Volume Extraction feature creates a bounding box based on the dimensions specified by the user and automatically extracts the fluid region inside the solid geometry. Now, let's move on to defining the material properties and analysis settings. For CFD simulations, fluid and solid material data must be selected from the materials labeled CFD in parentheses. When selecting CFD fluid materials, you can choose from a variety of fluid property data. For properties, since we are performing a 3D simulation, click 3D first, then move to the 3D CFD tab and add the air material property that we created earlier. Then, shall we generate the 3D mesh? Click the 3D tab and select the target flow domain. Then, configure the mesh size settings and activate the checkboxes as shown on the screen. After selecting all target regions for mesh generation, make sure that the properties have been correctly assigned. Then, click the arrow on the right and enable geometry proximity and avoid tetra with all boundary nodes to create a higher quality mesh. Now, mesh generation is complete. Let's make sure the mesh is generated well inside the model by using clipping plane function. Now that mesh generation is complete, let's move on to setting the boundary conditions. Let's configure the inlet, outlet, and wall boundary conditions of the flow domain as shown on the screen. Click Inlet and Outlet in the CFD Analysis tab at the top, then define the inlet and outlet separately. For the inlet velocity, enter a value of 2.5. For the outlet, select the surface where air exits and click OK. At this time, be careful not to include the inlet and outlet surfaces when setting the wall boundary conditions. Once the boundary conditions have been added to the LBC tree on the left, enable mesh visibility on the screen and proceed with monitoring setup. Monitoring is highly recommended because it allows you to output calculated physical quantities from selected nodes, surfaces, or volumes during the simulation analysis. Now, we're almost done. Let's move on to creating and configuring the analysis case. Since this is in general fluid flow analysis, make sure that only fluid flow is checked and verify that an appropriate turbulence model has been selected in the module settings. If you right-click Analysis Case in the Analysis and Result tree on the left, you can see several predefined analysis types. From here, create a steady-state CFD, then click Edit. You will then see an analysis setup window like the one shown on the screen a moment ago. Before running the simulation, save the NFX file to your preferred location. Once the file has been saved, go to the Analysis tab and click Perform to start the simulation. Make sure the analysis case created in the previous step is selected, then click OK to start the simulation. Now that the simulation is complete, let's evaluate convergence using the CFD graph. In general, convergence is considered achieved when the residual values decrease sufficiently and the monitoring values remain stable. However, please keep in mind that you should always verify the actual physical results carefully before making a final judgment. Now that the simulation is complete, shall we take a look at the results? In the Analysis and Result tree on the left, you can review the results for each calculated step. Double-click Total Velocity or Pressure, then click the Multi-Step Animation Recording button at the bottom to observe contour changes throughout the calculation process. Also, please remember that by clicking the Save button, you can export the results as a video file. You can also view vector plots by disabling the contour display in the upper left corner of the Results tab and selecting Slice Plane Vector in Vector tab. You can also visualize streamlines by clicking Flow Path in the Fluid Analysis tab. The number of samples and line thickness can be adjusted freely, and the number of arrows can be controlled by changing the division number. Next, let's check the maximum and minimum values, as well as the results at specific locations. Click Min-Max in the Results tab to automatically display the maximum and minimum values of the currently displayed result. If you want to check the value at a specific location, use the Probe tab. Simply select the desired node, and the result value at that location will be displayed, making it easy to investigate the analysis results in detail. Now, let's review at the analysis results obtained from the simulation. In addition to velocity contours, pressure contours, streamlines, and vector plots, NFX provides a variety of post-processing capabilities. We will introduce these advanced post-processing features through additional examples in future tutorials. While following along with today's practice, please make sure to remember these key points. How was today's lecture? Simulation may seem difficult at first, but if you follow the steps and practice hands-on, you can get started with confidence. With MIDAS NFX, learn the fundamentals one step at a time and challenge yourself with a variety of simulation examples. Then, see you again in the next video. This has been Mighty, your hands-on practice assistant.